Okay, Stefano, thank you very much for your introduction. Hello, everyone. My name is Bartusiak. I'm a research associate at Fraunhofer IOSB, which stands for Institute of Optronics, System Technologies and Image Exploitation. And I would like to briefly show you, present to you our portable cybersecurity training and research platform for power grids. Before I do it, I would like to just drop a few words on our current project within this platform. It's been created, and then I will give you a slight insight on the background, the architecture of this platform, and what do we use it for actually. And as a last point, just a short demo of an attack that we've implemented for this platform. So yeah, let's just step in. So the project that I'm currently working at is called Cybersecurity Training Lab, and it's a cooperation between different multiple Fraunhofer institutes and universities of applied sciences in Germany. And the main goal of the project is to raise cybersecurity awareness amongst in the specific fields of industry. The way we do it, we just develop, create, and perform different training courses in this area for specialists and executives in the industry and public administration. So there are 6 main topic areas, which you can see on the left down corner. My consortium is responsible for IT security for energy and water supply. So simply saying for critical infrastructures. And very important part of this project is the fact that we've created mainly stationary laboratories that are placed among different Fraunhofer Institute locations, which are used to enable participants to do some hands-on exercises, practical exercises during the courses, during the trainings, and try out different attack scenarios or different defense concepts directly on some hardware and virtual tools that are like built there. So one picture you can see at the top is just an part of a laboratory for the industry 4.0, just a monitoring wall. At our consortium, we've created a stationary laboratory where we are able to simulate the entire power grid and integrate also real hardware via so-called power hardware in the loop environment. But beside this, another project that we've done is creating such mobile platform so that we can also use it for some other purposes. We can move it from one place to another. And the idea here was also to create some kind of an environment where physical energy supply process can be simulated, but only on a smaller scale. So in this case, this platform represents an local adjustable grid transformer with tap changer. So the main process is about the voltage regulation. And it consists of common automation components that are used in the industry, in the energy industry, circuit breakers, sensors, actuators, HMIs, PLCs, which are all interconnected via common communication protocols used in the energy context. So a typical ISC 61 8450 or ISC 60875 104. And also, of course, very common Modbus protocol. Yeah, so beside this automation technologies that we have here, we've got, of course, like for the interconnection, the common ICT infrastructure, like firewalls and switches, which I'm going to like show you in a second. So how this platform is designed? Basically, there's this main process going on, which is the regulation of the voltage. We have an input side with a sensor, voltage sensor, giving us an input voltage over the PLC1. We've got the output side with a consumer side represented by some sockets and a light bulb, with our output voltage and our step transformer that is supposed to regulate the voltage according to what input voltage is. In the real world, we are talking here about the medium voltage that is slightly fluctuating, oscillating. Of course, in our platform, we could not use like medium voltage, so we have also like 230 volts as input, and some extra transformer that is doing this fluctuation for us. It's control over Raspberry Pi, and it's just generating some slight oscillations. You have HMI in the middle for controlling and monitoring, and some other components like for the analyzer, circuit breaker, and so on. Here's another view, how you can so that you can better imagine how the process looks like. Basically, we've got an input voltage measurement, as I said before, which is just done by this analog voltage sensor, and the values are passed to the PLC1, and then further to our monitoring console, HMI. On the left side, we have the input voltage. We have two Raspberry Pi screens, which are just illustrating the Modbus data traffic. We have the Modbus communication at the moment. On the other side, we have the output voltage measurement, which is also like passed to the PLC2 and also to the HMI on the right-hand side. But PLC2 is also responsible for controlling the process. So as soon as there's some voltage changes, it's just using our step transformer to regulate the voltage, so that on the output side we have always 230 volts. So that's always in this green area here. Yeah, HMI, as I said, just displaying the current process status. There's also a manual mode, so it can be controlled also by hand over the HMI.
Joseph, may I ask you if the PLC are Beckhoff?
These are Wago. VAGO, this is a German producer.
Because it's a Modbus.
Yeah, but yeah, multiple PLCs support this protocol, so it's quite common. Okay, so this is how it looks like as it's working. So on the left side, you can see like fluctuating voltage that is more than 230 volts. You can see it also on this left-hand side on the input voltage. And on the right side, we have our PLC that's controlling the process and trying always to keep 230 volts as output voltage, so that this light bulb is constantly lighting. Yeah, and you can see also the Modbus traffic going on here on the above Raspberry Pis. Simply, sending the control commands or reading the voltage measurements. Okay. There you can see this is our step transformer that is responsible for the main for the process, and this is the transformer controlled over this Raspberry Pi that is only used for our input simulation of this voltage fluctuation on the input side, so that the controller has something to do here. And you can see also like different industrial switches and firewalls that are also like built here just for training purposes to try out different manufacturers and different configurations, network configurations. on the left side, which there's this circuit breaker and power quality analyzer, which I'm not going to talk about within this presentation. So what are the application scenarios? There are main two scenarios, as I said before: training courses providing some hands-on exercises for the participants, where they can really see what it really means when attacks are being performed and how they can really disrupt an attack-occurring physical process. We've got like 3 types of attacks implemented. And then we've got, that's the one side. The other side is the side of the defense, and participants can also do many tasks preventing these attacks. So they can test out different defense concepts and implement different measures, mainly based on the defense in-depth concept standardized by IEC 62443 standard, what Stefano already meant. We used also as a research framework at the moment, and we are trying to apply cryptographic methods for securing the communication on this platform, because all of these protocols that I went before are not cryptographically secured, and they're like in plain text. Data is just being sent out in plain text and can be manipulated. So there's also an extra standard for this. IEC 62351, which we are like also examining and trying to determine how the application of cryptographic methods is influencing actually the communication, because in this energy context, there are like big important requirements concerning the real-time communication with like 4 milliseconds of read and response sequences, which is then might be problematic when we are using some encryption methods here, for example. And the other thing is evaluation of IDS techniques in the ICS environment. This is also another part we are investigating using this framework. What's worth to mention is this physical environment, this platform can be extended over some virtual part. This is what how we've done it. Beside our platform that is representing our process zone with its own area network. We've built a virtual environment with 2 virtual machines representing our office network environment, and some simulating internet, like external network, where also a hacker laptop can connect it. And in order to illustrate what are the strategies, how can be systems compromised, and which coupling points can be used to move along the network down to the process LAN, we are just using cyber glitching steps to show the participants how this can be obtained. So we are generating some payloads in the Metasploit environment and upload this into the server, and then we use different propagation ways, and either as a phishing email or the rubber ducky USB stick, just to compromise the first PC, and then establish an interpreter session with the attacker laptop, and then move along on this network till the point where we are getting to our process LAN, and where the 3 different attacks can be used that I mentioned before, towards against the platform. So just as a last part, quick demo of man-in-the-middle attack, which we are also performing during, actually the participants are performing this themselves just to understand how such an attack really works. As I said before, it's based on the Modbus communication. So here you can see actually there are like two main commands or two Modbus functions being used for the communication, which is just reading the measured values, reading the voltage values on one hand side, and and then issuing some new commands, control commands on the second hand. On the other hand, just to stepping up or down the transformer, just to regulate our output voltage. So the man-in-the-middle attack is based on the RP spoofing. Of course, we assume the attacker has already gained access to the platform, so this process local area network, and here's just rerouting the traffic to his own computer and manipulating it accordingly. So what he's actually doing here is issuing his own commands to step down the transformer so that the output voltage goes to 0. On one side, on the other side, he's also manipulating the measured value so that the operator, when looking at the HMI, cannot really tell any difference that there is an attack or any suspicious action going on, because the readings are going to be correct. So last two slides. This is the video that I'm going to show you, and just a few hotspots to look at. First is the output voltage. You're going to see that the voltage is not going to be changed, even though the real reading of the voltage is going to be 0. The voltage readings on the Modbus side are also going to drop to 0, because this is the traffic shown before it's getting manipulated by the attacker. So you're going to see that the light bulb is going to go off, and the sensor is going to show 0 volt. And on the right-hand side, you're going to see the attacker laptop with an attack script getting run, including RP spoofing. Okay, so last slide, just this quick demo. So now the attack starts, and you can see the transformer is going really down back to 0. The voltage readings in this our Modbus screen also show low values, but actually on the HMI side, there's the last correctly read value still being displayed. I can show you this maybe again. And this is one of the attacks that we've created here. Okay, I'm done with my presentation. Thank you very much for your attention. So I'm open for questions.